welcome to your subject Theory of Structures 1. Okay, so we will be starting with our Module 1, which is the Introduction to Structural Engineering. And then in this module, we will be discussing 3 units. Okay, the first unit is the Analysis and Design Process. We are going to understand what is the Analysis and Design Process. So in this unit, this is your unit learning outcome. So first is to enumerate the Analysis and Design Process, and then to understand each step, and then relate this one with each other. Okay, so that is our unit learning outcome in this unit. Okay, so we are going to understand each and every steps of this design process, and then we are going to relate. We should be able to relate with this one with each other. Okay, so this is now the steps or the process itself. So we have here the planning phase, preliminary structural design, loading computations, structural analysis, safety and serviceability check, and then finally the revision and finalization of the structural design. So the planning phase, that is the fundamentals, okay, such as the purpose. We are going to define what is the purpose and the function of the structure itself, and then of course at the same time we need to satisfy the preferences of the clients. And then using those purpose and the preferences, we are going to generate and lay out the dimensions of that. If that is a building, then we are going to lay out and then indicate the dimensions of this structure. And then of course at the same time, this is where we will be deciding what is the possible structural system that we are going to apply. If we say structural system, that is the type of the skeleton type of the structure that we are going to use. There are a lot. It will be discussed on the higher subjects. Okay, so but I will just be mentioning some. Okay, one, there is reinforced concrete moment resisting frame. Okay, just like that. And then you can have their steel moment resisting frame, and then there are sub types of these type of systems. So there are a lot, or it could be a combination of both. So that is what we call as the structural system. So we are going to decide based on the layout and dimensions, and based on the function, of course, we are going to decide what is the structural system for us to use. And then at the same time, deciding your structural system, we are going now to incorporate the type of material we are going to use. So types of material could be concrete, steel, could be timber, or it could be others, or it could be combinations. Okay, and at the same time, we are going to establish the location parameters. If we say location parameters, that is the setup or the characteristics of this specific site where we are going to erect the structure. Okay, the proposed structure. So what are the important things there to include in the location parameter is the soil strength, or that is the soil parameters. Okay, the properties of the soil. So that is important. Earthquake zoning. Okay, since here in our place we are prone to earthquake, that is also very important requirement. And then wind velocity. Okay, the same thing with wind velocity. Okay, and then the and as alike. Okay, as required by the, of course, by the project itself, and of course other things to do. So if you will try to rate this one on actual project, let's say the project is a building, this is now preparation of the architectural plans. Okay, in collaboration with the other professions, since we are of course on the side of the structural designer. We will collaborate with the architects, we will collaborate with the other fields of engineering, just like the geotechnical, the one in charge on the soil parameters, and then of course the electrical, okay, the electrical wirings and setups, mechanical if we need there, if we have a machine in our, or yes, machinery in our building, and so on and so forth. Okay, plumbing and so on and so forth. So that is the planning phase. Okay, then once we are already done with that, then we will proceed with what we call as the preliminary structural design. So this is a structural design which is preliminary. If you say preliminary, we are going first to assume. Okay, we are going to assume. So sizes of structural members. So okay, so once we decide now what type of structural system and what material, then now the next thing for us to do there is to assume. Okay, assume what will be the sizes. What will be the sizes of the posts, the beams, the slabs, and so on and so forth. That will be our preliminary design. We are going to assume. So we are going to establish, okay, these sizes in relationship to your planning phase, of course, with the planning phase that we did before. So sizes are usually based on the approximate analysis and must satisfy code and code requirements. Okay, so experience or past information plays a big role. What does that mean? So of course, doing this preliminary structural design, we should satisfy the existing building codes. Okay, if you say building codes, this is the guide of the designers. Okay, so if on our side as the structural designer, we have what we call as the Structural Code of the Philippines, or National Structural Code of the Philippines. That is the NSCP. That is actually updated, okay, updated or revised from time to time, and the latest that we have up to right now is 2015. That is the 7th edition. So that is what we are following. Okay, with the requirement, there is a minimum sizes and then a minimum strengths. Those are encoded, or those are part of the code that we need to follow. And then of course it says there that experience or past information plays a big role. So this is important, especially if you are already an experienced structural designer. You can make use of your experience previously in designing similar structures for you to assume the preliminary sizes. Okay, since again later on we will be assuming right now, but later on we are going to analyze that one and prove if that is capable of handling the loads applied on the structure. If not, then we need to revise that one. So those are the next phases or next steps. So essentially, preliminary members dimensions are assigned to have a basis for loading computation. So again, that is the use of the preliminary sizes for us to have a basis in the loadings, because if we will now proceed to the next, which is the load computations, that is what we will be using. Given the size and the type of material, we can now compute the weight of that. Let's say that is a beam, then we can compute the weight of that beam. So that is what we will be using as the load itself, in addition to the other external loads. Okay, so with preliminary sizes, structure, function, or purpose established. Okay, so given these sizes, and of course we already established what is the function or purpose of that structure, other factors considered in previous phases, loadings can now be established. So as I've said before, okay, so we already prepared what we need in this step previously, especially on the preliminary structural design. We prepared, okay, we assumed, and what we assumed as the sizes, that is what we are going to use here in the load computation. So it says there the 7th edition of National Structural Code of the Philippines, that is the NSCP 2015, as I've said, that is the latest code that we are following. Okay, defines loads as, okay, so that is how it defines loads: forces or other actions that result from the weight of the building materials. So that is what I'm saying. That's why we need to have the preliminary sizes. Okay, the weight of the building itself, and that of course includes the weight of the members. Okay, if you say members, the beams, columns, the slab, and so on and so forth. And then occupants. If you say occupants, these are now the one occupying the building. If that is for an office, then the occupants are the person itself, or the people itself. And then in their possessions, okay, whatever additional that is there that we need to consider. Environmental effects. If you say environmental, these are now the earthquakes, wind, and so on and so forth. Okay, if there's a snow, then that is another thing to consider. Differential movement. Okay, we have what we call as the allowable settlements and so on and so forth. Okay, allowable based on the codes. So we need also to consider that one as additional load. And restrained dimensional change. Okay, permanent loads are those loads in which variations over time are rare or of small magnitude. Okay, so actually we can classify loads in terms of its state. Okay, there are loads which are applied stagnantly. Okay, or that is a fixed load. Okay, we call this one the dead loads. Okay, it is not being affected by time. Okay, and there are loads which are affected by time, just like the movement of the people. That is what we call as the live load. Okay, so all other loads are called the variable load. So one of that is the live load, and one of that permanent load is dead load. Okay, so that will be discussed once we will go on the loadings itself. And then next there, once we already computed the loads to be applied on the structure, we are now going to analyze this one. So if you say analyze, based on the assumption of the sizes and of the type of material on your building, we are going to analyze if that is capable of handling the loads based on what we computed in step number 3. So that is now the structural analysis. So in building codes, okay, as one of the requirement here in the Philippines, before your plans will be approved by the building officials, you need to attach this structural analysis. If you say structural analysis, that is the basis. Okay, that is your what do you call this one? That is your proof. That is a backup of your design. Okay, so that it will now say there that I computed this one based on what is available. Okay, based on what is available. I did not just guess the sizes, and I did not just guess the type of materials or the strength of materials. That is shown on the analysis. So that is the solution, proving your design. Okay, so given the loadings are established, analysis is carried out to establish stresses. Okay, so that's what I'm saying. You're going to prove that one by means of solving. Okay, so we will now be establishing stresses using shear and bending stresses, most common among others, to be resisted by members. So deflection and other parameters of interest in terms of serviceability requirement may also be established. In structural design or any technical procedure, there may be systems, okay, are often idealized into simpler models to facilitate analysis. So this is now important. Okay, in actual scenario, the building, let's say that is a 5-story building, the framing of that is actually complicated for us to analyze as a whole. So we are going to cut that one. Okay, we are going to cut that one into parts, and then we are going to analyze it part by part. Okay, so this part by part analysis, or you are going to separate a part of that total structure, we call that one structural models. That will represent the scenario on the entire building. Okay, and then these models are not exact representation, as I've said. These are not exact representation because that is just a part. Okay, that is not an exact representation of the realities of the system by itself, but okay, represent the system to a point where the purpose of analysis can be satisfied. So we are doing that. That is what we could closest to the actual scenario. Because if you are going to do it as a whole, that will be too complicated. And even that's why we have what we call as established softwares, wherein it is made to analyze a complicated building, but actually in making that software, it is still the same thing. The analysis is done part by part, and then it will be combined, and then that is now the program made for the analysis. Okay, so that is structural analysis. So simply it is showing the proof, the calculations as a proof of your design. So again, once you have the preliminary design, that is step 2, now you are going to compute the loads to apply on the structure, and now you are going to analyze, prove if that preliminary size is possible for this kind of loading. If not, then that is now, but before going to that, okay, we need first, at the same time, together with the analysis, we need to apply first this safety and serviceability check. Okay, common serviceability check include differential foundation settlement, deflections, durability, fire resistance, and other parameters that may be unique to the structure depending on its function. In general, serviceability requirements are requirements that must be satisfied so as the functionality of the structure is not hindered by factors outside the safety or strength of the structure. So what does that mean? Okay, it is not just enough for us to analyze if it is capable of handling the loads. Okay, we need also to take into consideration the comfort. Okay, the comfort within the structure. So let's say you are one of the occupants of the building. You need to be comfortable. It is not just enough that the building can stand. Okay, it is also important for the occupants to be comfortable. Okay, so that is what we call as the safety and serviceability. So you are comfortable at the same time. I mean, you are safe in that structure at the same time you are comfortable. Okay, so that is the safety and serviceability check. So that is again a part of the code that we need to follow. For example, there is the differential foundation settlement. Okay, it could be allowed that once you will erect the total building and that will be occupied already, it is allowed that there will be a slight settlement. If you say settlement, there will be a slight movement, or yes, settlement, a vertical displacement of the foundation, okay, of the entire building. There is an allowed deflections or settlement. What I mean with that, okay, settlement. But that should not exceed the maximum, because once that exceed, that might now affect the strength or the safety of the total structure, or that might now affect the what we call this one, comfort of the occupants. Okay, if you say comfort, maybe the building can carry that one once it will lean because of settlement, but now the occupants is not that comfortable already, because of course your building is already leaning. Okay, so deflections, durability, about fire resistant. Okay, those are important things. Of course, these are also a part of the building codes. If you are going to let your design be approved by the building officials, they are now going to require that your structure is fire resistant. So there should be a part of that plan that should be what we call this one, certified, okay, by a personnel which is expert on fire resistant structures. Okay, and other parameters. So that is the safety and serviceability check. And then finally, as I've said a while ago, once you are done with the structural analysis and you proved that it is not enough, okay, the preliminary assumed sizes is not enough within the given loading, or at the same time it did not met the safety and serviceability minimum requirements, then we need to revise. Okay, so we need to repeat the process starting from the preliminary design, structural design. We might be changing sizes and so on and so forth there, or the strengths, and then reanalyze. If we are going to repeat that one again and again and still nothing, we cannot finalize the structural design, maybe we need to go back to the first step, which is the planning. Maybe the plan is not possible, so there might be a slight revision on the plan, okay, for the project to be possible. Okay, so that is the process. So step 1 is planning, and then preliminary, and then you are going to compute loads, and then analyze, and then check the safety and serviceability. Repeat this one up to the time you will now have the final structural design. And then once you have that, there will now be the finalization. Okay, so that will now be detailed properly, and then completely, and that will now be included as a part of the plan. So we have what we call as the architectural, that is the view, that is the statics. Okay, that is the concept of the structure. And then you will now attach there the structural. Structural means that is the plan, the distribution of the beams in columns, and at the same time the sizes is indicated there, and how it will be constructed. Okay, so that is the structural plan. Okay, so again, you have there the concept, that is the architectural plan. If we are talking about a building, okay, you have there the concept, okay, but that will not stand without the structural. So that is how important this structural design is. Okay, and this subject, theory 1, is actually the start of that structural analysis. Okay, we are going to learn how to analyze structures, different types of structures. Okay, so the results of the analysis are then used to check the decisions made during the preliminary design phase against code serviceability and safety requirements. In the event that the preliminary design will not be able to support said requirements, preliminary design is carried out again. Okay, so that is what I'm saying. We will be repeating the process, and thus new loading computations and new set of analysis is done until a satisfactory design is reached. So that is now the complete process of analysis and design, okay, of the structure. So that's it. That is for Unit 1. Now let's proceed with Unit 2. What are the types of structural forms? Okay, what are the structural forms that we will be using in structures for us to erect and structures? So in this unit, these are your unit learning outcomes. So know the different types of structural forms. Understand how each type carry or resist applied loads. Okay. So we have here the common. Okay, there are a lot actually of structural forms, but I will just be explaining I will just be discussing the common. Okay, the commonly used structural forms. So we have here beams, frames, Okay, and in frames we have what we call as the plane frame, and then we have what we call as the space frames. And trusses, we have what we call as the plane trusses, and then we have what we call as the space trusses. So actually this is an example of beams. Okay, that's an example of beam. We will discuss that one on the next slide. Frames, okay, and then trusses. We will discuss this one on the following slides. So let's start with the beams. Okay, a beam is a structural element primarily carrying lateral loads. So if we say lateral loads, okay, that is the orientation. For example, okay, look, these are now examples of beam, types of beam. For example, this is the beam. If we say lateral loads, the loads are perpendicular to the axis of the beam. Okay, since this is horizontal, then the loads are vertical to the beam. Okay, beam deflects by bending, which result to bending stress. Okay, so maybe this is now introduced to you in your mechanics. Okay, so if this will deflect, we have what we call as the, or if that will bend, we have what we call as the bending stress, which is a type of stress that is a variable. Okay, deflection depends on the type of support and orientation of the loadings. Okay, so we have now these types of beams with respect to support. So this is a cantilever, okay, that is a fixed support on one side, and the other side is free. Simply supported, okay, we have simple supports. If we say simple supports, that could be a ruler. If we say ruler, that is just restricting, perpendicular to the axis. And then hinge, the second, the other side could be a hinge. Okay, if we say hinge, that is restricting, perpendicular and parallel to the axis. Okay, we have overhanging. Okay, so this is the overhang. If we are talking about overhanging beams, this is the part of the overhanging. Okay, just like the cantilever, but the difference is that in cantilever the protruding part is supported at a fixed support. This one is just it is just like a prop. Okay, it is protruding at the prop support. Okay, and then continuous, it means that is continuous. So that is the scenario. Okay, we have what we call this one, intermediate supports in between. Okay, and then fixed end, both are fixed, and actually this is the most common scenario of a beam, because that is connected to a column. If we are talking about a reinforced concrete, wherein they are constructed rigid on both ends, so it means it is now a fixed end, both ends. And then we have a cantilever, so simply supported, or that is what we call as the prop beam. Okay, prop beam is actually, or this cantilever simply supported beam is a cantilever beam which is on the other side simply supported. Okay, or we sometimes call this one as a prop beam. So these are the types of beams. So if you are going to load that one laterally, that will bend. That will bend as a reaction of the load. Okay, as it carries the loads. Okay. Second common structural form is the frame. So structure composed of combination of beams, columns, slabs rigidly connected together to resist an applied load. Okay, so that is your frame. It is now a combination of beams, columns, and slabs. Okay, columns are actually, what is the difference of beams and columns? Beams are actually mainly loaded laterally. So the main loading of beam, so this is an example of beam. The main load of a beam is lateral. Okay, the column, if we say column, that could be loaded laterally, but the main thing or the main load here is axially. Okay, the difference of column and beam is that in beams there might be an axial load, but that is negligible compared to the lateral loads. But in the column, the main loading is axial. But in column also, that could be axially loaded or at the same time laterally loaded. Okay, for example, again, you have an earthquake load, so that is a horizontal loading. So that is the lateral loading of the column. Okay, so that is a column and beam, and of course slab. So if you try to look at this space frame, or again, this is an example of 2D frame, okay, or plane, two-dimensional frame. This could be a simplification of a 3D frame. Okay, 3D is a space frame. Okay, so if you'll try to consider a space frame, look at this. There is a slab. The slab is this one. Okay, a plate. Okay, so that will serve as the ceiling, and of course this is the base of the floor. So that is the slab, and we have here a beam, the horizontal elements, and then the vertical elements are the columns. So in addition to that, we have what we call as the foundation. Okay. So if these are now connected with each other rigidly, if you say rigidly, that is now fixedly supported or fixedly connected with each other, then this is now considered as a frame. Okay. It could be, again, it says there that a complex space 3D, or that's a 3D frame, can be cut and simplified into a plane frames, or that is a 2D frame, to simplify the analysis of the whole structure. So as I've said, okay, we cannot analyze this as a whole because that is too complicated. So we are going to simplify that by separating this into an analysis model. Okay, we have what we call as the analysis model. That is what we are going to analyze, the model that we are going to analyze. So we might be simplifying that one. Okay, we might consider one of these side, and then that is the 2D frame, and then consider another side, that will be another. Okay, so that is the frames. Again, that is a combination of beams, columns, slabs, or it could be a combination of different members, as long as they are connected rigidly. Okay, they are fixedly connected with each other. So by the way, what is the scenario of a rigidly supported or rigidly connected elements? For example, is a reinforced concrete. Okay, that is being poured, okay, at the same time. So it means if that is a concrete, that will cure as one. The beam, the column, and the slab will cure as one. So they will become one single element helping with each other. So that is the key point in your frames. Okay, because we can relate that one if we will go to the next one, which is the trusses. Okay, a structure composed of pin connected members under pure tension or compression. Trusses are assumed to be loaded on joints only so as not to create a bending stress on its members. Okay, so this is the difference, as I've said, the difference of a frame and truss because of its connection. In truss, it is the same. There is a 2D truss or plain truss. We have a space truss or 3D truss. Okay, the difference of this truss with the frame is the connection. In frame, that is fixed connected. In trusses, that is pin connected. If you say pin connected, okay, if you say pin, the reaction there is only two: restriction, horizontal, vertical, if that is oriented that way. There is no moment. It will not resist. The support will not resist rotation. So there is no bending. That's why it says there that for us not to create a bending stress, the assumption of truss is that that is always loaded on the joints. So, okay, let's consider an actual scenario. Let's say this truss is carrying, this part of the truss is carrying an entire load. Okay, the entire part of the truss is carrying load. So maybe that is a uniformly distributed load. We are not going to analyze it that way if that is a truss. We are going to transfer this uniformly distributed load into a concentrated load at the joints of this truss. And then that is how we will, before we will now start analyzing it. Because in trusses, that is now, since if these are simple supports or that is simply connected or pin connected, then it means there should be no moment within your member. And that is true because if we will be loading all of this into the joints. All the loads will be applied on the joints. Okay, so the same thing in here. Look at this, the example of that are just like this. Okay, it is a framing or a truss of a bridge. Okay, this is a space that is a 3D. And we can simplify that actually, the same thing, just like frame, we can simplify it into plain truss. We can cut one section and consider that one. Okay, but there are some cases wherein the truss is too complicated for us to simplify. Okay, just like this. This is an example of a complicated space truss wherein it is hard for us to be cutting this into a simplified 2D truss. Because look at this, if I will cut that way, that will be different in the other sections. So this might now be analyzed as a whole by using, of course, what we call this one, an application or a software, I mean. Okay, since that is already too complicated to be calculated manually. But if we are now solving just like this, okay, this one could be simplified. This space truss, this type of space truss can actually be simplified into a plain truss, so that you will be having a simple truss there, and then you will be loading that one, and then we can actually analyze this one. okay, as a whole. Okay, and then once you already have the analysis, you can now go back and then correlate that one with the entire space 3D truss. Okay, so those are the commonly used structural forms. But we have here other types of structural forms. One there is arches. Okay, structures composed of compression curvilinear members resting on supports. These are used to large span constructs or structures such as airplane hangars and long span bridges. Okay, so that is an example of arches. So we have here two hinge arc. That is a complete arc, and then we have here supported with pin. Okay, and then we have here the 3 hinge arc. So at the middle there is a hinge, that is a release. Okay, a release point of the moment. And then we have here a fixed arc. Okay, so that depends on the function or the orientation on the actual scenario. So we have here cables, flexible elements that support the applied transverse loads by a tensile resistance developed in it, commonly used in suspension bridge, transmission lines, and several other engineering applications. So this is an example of a cable. Okay, this is an example of a cable. Cable is a pure tension. Okay, pure tension element. Since that is flexible, it cannot resist compression load, because if you are going to apply compression load on a flexible element, that will bend or that will crumble. Okay, so that is the use of cables to resist tension. So these are commonly used on suspension bridge, just like this, or in transmission lines. Okay, shells. Okay, so these are actually these are now, okay, some of these are used before on the what do you call this one, earlier era, but some of these now are being used as the what do you call this one, modern designs, just like the shells. Those are now modern designs. So this is a shell, a curved plate structure shaped to transmit applied loads by compressive, tensile, and shear stress. So that will be curved in such a way that it will resist the load. Okay, so again, at the same time, of course, since that is the common, this is now the modern designs of architects to have a good aesthetics on the structure, is for them to provide curves. But at the same time, that is not just the function of the curves. The curves is to adjust for the type of loading. Okay, maybe that is now carrying. In this place, it might be having a large, okay, wind load. So you might be creating curvilinear structure so that it will not trap the entire pressure of the wind. Okay, so there are purposes of each of these structural forms. So these are now again the others, but the commonly used, especially on buildings, okay, are the beams, frames, and trusses, not just buildings and other types of structures, just like bridges. Okay, so those are the structural forms. Now let's proceed with the unit 3. Okay, that is the final unit in this video or in this module, is the loading conditions and building materials. Let's try now to talk about the loadings and then the types of material used. Okay, so in this unit we have these outcomes. Okay, understand the loading conditions and familiarize yourself with some of the load combinations from different design approach. Understand the behavior of each type of building materials. Okay, now types of loads common in most areas. So these are now types of loads common, but these are not all. Okay, there are others. There are what we call special loads. Okay, it depends on the type of the structure, especially those special structures. Okay, if you say special structures, these are just special for that certain purpose. Okay, unlike the common, if you say common, the common structures are buildings, bridges, pavements. Okay, those are the common structures. Okay, the example of a special structure is tower. Okay, that is only intended for its purpose as a tower. Okay, so what are the loads? Okay, that could be categorized into two: gravity loads and lateral loads. If you say gravity loads, that is a vertical. The direction of the loads is vertical. It is going directly towards gravity line of action. Okay, in the line of action of gravity, that is where the load is directed. Okay, it means that is affected by the gravity itself. So lateral loads, these are now the horizontal loads. So for example of this, that will be discussed later on. Okay, so gravity loads These are some, okay, dead loads. So if you say dead loads, let's try to symbolize that one by the symbols. So dead loads is D, live load is L, snow load is S, wind load is W, earthquake load is E, okay, for the purpose of the load combination later on. Okay, so dead loads, these are permanent stationary loads primarily due to self-weight of structural members, permanent walls, fixed equipment, and weight of other stationary materials. So that is a dead load. So for a building, the main dead load there is the weight of the building itself. Okay, whatever parts of that could be structural members, that could be a wall, that could be a fixed part of the structure. So these are all the dead loads. Okay, so now the next there is the live load. So live load, it means live. Okay, movable or moving loads, or these are now variable loads, produced by the intended use or occupancy of the structure, including weights of occupants and moving partitions, and so on and so forth. So that is what I'm saying, that is the live load, a variable load. From time to time, it is changing. It is affected by time. So for example, we are talking about the occupants, the person, okay, as the occupant, that is moving within the area. So the loading is not fixed in this point. So that is a live load. Example, let's say movable partition. If we say movable partition, that is a partition that can be moved or that can be transferred in different locations. Okay. What else? Moving loads. Example, tables. Okay, maybe this is an office. Next time, we might rearrange the office. So those are now considered as movable loads. Still live loads. Snow loads. Okay, these are special type of gravity load applicable in areas where snowfall is possible. So actually this is in addition to dead load, but of course the approach of snow is that it is not that permanent. It is not permanent. It is stationary, but it is not permanent. So that is of course applicable only on areas that there is snow. Okay, there is no snowfall. And then now let's proceed with the second type, horizontal loads. Okay, those are now perpendicular to the gravity loads. One is the wind loads. Okay, so for example, this is the building that is blown by a wind. So the direction of the wind is perpendicular to the axis of the vertical axis of the building. Okay. So wind load is caused by movement of air relative to earth. This load is formed due to wind pressure received by the exposed surface of this structure. So wind loads actually depends, the amount of the load, this type of load depends actually on the area of the surface area of the structure that is exposed to the wind. Okay, wind is a pressure. Okay, it is a pressure, it is coming as a pressure. So whatever area that will receive, okay, that will catch that pressure, whatever pressure catched by the area will be converted into a force. Okay, and that is the lateral load from the wind. Okay, so that is the wind loads. Earthquake loads, okay, caused by the ground motion induced by an earthquake. Okay, several factors affect this type of loading, such as the intensity of ground shaking, properties of foundation soils, etc. This is a little bit complicated type of loading. So actually, there's a separate subject for the for understanding totally the behavior of an earthquake to a structure. Okay, so we have what we call as the engineering, earthquake engineering. Okay, that is where we will try to get to know the earthquake. But for the meantime, okay, if you say earthquake load, that is actually moving your structure. So once the structure is moving, we have now an acceleration. Okay, we have now an acceleration. We call that one the earthquake acceleration, or the acceleration, motion acceleration. And since there is an acceleration, and of course the building has a mass, from mechanics or from dynamics, okay, from dynamics of rigid bodies, if there is a motion and there's a mass, then there should be a force. Okay, force is equal to mass times acceleration. So because of the movement of the building, the acceleration of the building, and then because of the mass of itself, then that will create a force, an internal force being resisted by the building itself. So that is an earthquake load, and that is being affected by a lot of factors. For example, as stated here, is the intensity of ground shaking. Of course, that depends on how fast the ground is shaking, okay, and how big the shaking is. And then properties of foundation soil. For example, what type of soil is beneath that structure? Is that soft? Is that hard? Because that type of or that property of the soil affects the original acceleration on the source of the earthquake, the soil will affect that one before it will reach the structure that we are considering. Okay, so that's why, as I'm saying, earthquake loads or earthquake, understanding earthquake is a little bit complicated. That's why there's a separate subject for that. Okay, so these are just the common types of loads on most of the area. There are others. Okay, for example, if your structure is exposed to fluids, then there is a fluids load. Okay, so that depends on the type. These are just the common. Now, these are now load combinations because, okay, we cannot say that the building is only under dead load. It is not only under live load. It is not only under earthquake. Because just like, for example, earthquake is not there every time. So by using statistics, the combination is derived empirically, okay, based on experiments and observations in statistics. Okay, a combination is made. So not every time there is a live load. Not every time there is an earthquake, there is a snow, there is a wind. So now we have what we call as the combinations. Possible, if you say possible combinations that might be happening. Okay, so we are going to predict that one. So these are now the combinations. We are going to add the possible combinations. We are going to add some of these individual loads, and that will now be what we call as the combination. So, but we need to discuss this. Okay, so there are a lot of approach in designing. Okay, there are a lot of approach which is established by, of course, previous professions. They established different approach of designing. And the common here is the ASD, or if you say ASD, that is the allowable stress design. Okay, this design approach uses the allowable stress on a certain type of material as the basis of calculating the load carrying capacity of the member, of course. Okay, so I will not be discussing this one detailed, this design approach that will be discussed in your design subjects. So let me just, this is just a introduction to this type of approach. So this approach of design is using the allowable stress. That's why it's called allowable stress design. Somehow this is related to the new approach, which is the allowable strength design. Okay, so that will be discussed on your design subjects. So what we will be using here is the allowable stress. If you say allowable stress, for example, this is a material. If you are going to test the capacity of that, you will have the exact capacity of that specific material. But that is not true to all of this type of material. Okay, there are factors that will affect. So we have what we call as the allowable. We will be only using a percentage of that. Okay, a percentage of the exact capacity. So that is what we call as the allowable stress. And that will be discussed again in your design subjects. So that is the first approach. Second approach is that we have what we call as the LRFD, that is the load resistance factor design. Okay, by itself, load resistance and resistance factor, we are now referring to factors applied on the loads. Okay, in here, the factor of safety is applied on the material itself, the strength of material. In the LRFD, the factors or the factor of safety are applied now on the loads. Okay, so what is the difference of that is that in this approach, we are now using the ultimate strength. If you say ultimate, okay, let's say again, based on my example a while ago, in testing this material, that is the exact capacity. That is the point before it will snap or before it will fail. But of course, we will not use that one exactly. Based on experiments, then that will be, we will calculate this ultimate strength. If you say ultimate, that is not actually exactly the breaking point, but close to the breaking point of the material. Okay, so ASD, in the allowable stress design, the strength that we will be considering is a little bit far from the breaking point of the material. In load resistance factor design, we are now trying to maximize the strength, so we will be going close to the breaking point. Okay, and that's what we will be using. Okay, so these are different. Actually, that is not just the explanation of that. There will be a lot. So again, that will be discussed in your design subjects. So that is the main difference of the allowable stress design and load resistance factor design. So in this different approach, these are now established combinations used in this approach. These are the combinations used in this approach. This is actually based on the National Structural Code of the Philippines, 2015, which is based on AISC, American Standards, okay, standard codes. This is the basis of our National Structural Code of the Philippines. Okay, so in this approach, these are the possible combinations. It could be purely dead load, there is no movement at all, purely the self-weight itself. And then second is the combination of the dead load and the live load. It depends. Again, I did not say that we will be using all of this combination on a specific element. Okay, there are elements which only be designed using dead load. There are elements of the structure which needs to be designed in addition to the dead load is the live load. Or there are other structures in addition to those. We will be considering what we call as the LR, that is the roof live load and the snow load. Okay, so those are the other combinations. So as you can see, these are the possible combinations. So as you can see, dead load plus live load, dead load plus, by the way, LR, that is a roof live load, the same thing, but the live load is on the roof. Or if you are not using that roof live load, if snow load is possible, then that could be a replacement. And then the fourth combination is the dead load plus the 75% of live load plus 75% of it's either the roof live load or the snow load. And then finally the dead load plus the 60% of the wind load. Okay, so that is the combinations under the ASD design approach. Okay, on the LRFD design approach, these are now the established combinations. As I've said, the factor of safety are applied now on the load. So as you can see, you have here multiplier which are greater than 1. So again, for us to have a factor of safety, if you say factor of safety, for us to give an allowance so that we will not compute this one based on its exact strength or in its exact situation, we will be applying an allowance, and these are what we call the factor of safety. So this is what happened on LRFD. The factor of safety is applied on the loads. While in ASD, okay, as you can see, the factor of safety, there are no more than 1 in this one. Okay, so it means that you just use the exact load. But the factor of safety is applied on the strength, so allowable stress. We are only using the allowable. It is a percentage of the total strength. Okay, so that is ASD. LRFD, again, as I've said, the factor of safety is applied on the loading. So as you can see, the dead loads here are multiplied by 1.4, 1.2. It means we exceeded the supposed dead load by 20%, by 40%. And in here, 1.6, or that is 160% of the live load. So we applied the factor of safety on the load. We magnified the load, okay, as an allowance to the actual scenario. So these are the load combinations by LRFD. 1.4D, 1.2D plus 1.6L plus 0.5 of the roof live load. And then we have here the 1.2D, 1.6LR, or that is the roof live load again. And then the F1L, F1 is actually just a coefficient which is depending on the live load. Okay, if your live load is less than 4.8, then you are using F1 as 0.5. But if your live load is more than that, or 4.8 and above, then you are using 1 as F sub 1. Okay, so again, it's either, this means that it's either you will be using this or you will be using that. That depends on which one will give a higher load. Okay, and so on and so forth. You can now read on these combinations. But okay, these are now the combinations. But for the sake of for simplicity, since we are still on the foundation or the start of the analysis, we will not be using all of this. We might be using only D. If we are using ASD, you might be using only D or D and live load, or we might be using only the first 2 or first 3 of the LRFD or the ASD. Okay, that is just for the simplification, since we are still on the foundation of the analysis. We are still to understand how to analyze. But once you will go now on actual design, you need to consider all these load combinations. It means that these are now the possible. These are now the possibility. One possibility is that this will happen, or this might happen. So for us to get the worst case scenario, we will now try to combine all of these using these load combinations and decide which one will give the maximum. That is the meaning of load combinations. It is trying to perceive the worst case scenario, so that we will prepare for the worst case scenario. Okay, so that is the load combination. And now we need to discuss also the most common building materials in construction. This is very, very important. We need to understand. But the discussion of each and every type of material actually will be discussed in your subject CMT, or that is the construction materials in testing. That is where you will try to understand the behavior of each and every material. But these are just for introduction. This is just introduction for each type of material. Okay, so these are just the common. Again, I will not be giving the all of the type, because of course there are a lot of types. I will just be discussing the commonly used in construction. So first is the steel. Okay, steel is one of the strongest building materials available with excellent tensile and compressive strength. Okay, so we know that steel is strong, very, very strong in tensile and compression. Because of its high strength to weight ratio. If you say strength to weight, the weight in relationship to its strength. Okay, so even if the steel is not that much, but the strength is remarkable already, or the strength is strong even if that is not much of steel. Okay, so that is the meaning of high strength to weight ratio. And the difficulty in its production, of course, the production of steel that will be milled into process, so that will be a little bit challenging or difficult. So because of that reasons, okay, but of course you will end up with the remarkable property. Even with this difficult production and then high strength to weight ratio, we still have we have what we call as the remarkable property, or the remarkable property that we are talking about is the strength. It is a remarkable strength in tensile and compressive strength or compression. Okay, so that is the challenge in steel, that the production is a little bit difficult, and this is an advantage. The strength to weight ratio is good, or is very good, excellent. However, that comes with its expensive cost also. So steel is a type of material that is expensive. Therefore, with this reason, the designer should consider an economical size and shape for a certain type of work. Okay, so that is now the reason why we have these different shapes of steel, isn't it? Why not use a solid one, or let's say a circular shape, a solid circular shape of steel, or a solid rectangular shape of steel as a column or a beam? Because again, as I've said, we have the strength to weight ratio, okay, is remarkable, that is high. So actually we do not need all of that steel just to carry this type of loading, and of course that is expensive. So it says that economical size, it means that is the least amount, or that is the possible least amount of steel that we can use to carry this specific type of loading. So as you can see, that depends also on the type of load, how the load is applied on the member. So we have here different shapes. Okay, we have what we call as the I shapes, channel shapes, angle bar, and so on and so forth. Okay, so actually this will be discussed again on your design subjects. Okay, so that is steel. Concrete. Second commonly used is concrete. So composite material made from mixing cement, aggregates, and water. Okay, so we have aggregates here. Okay, it could be sand, coarse aggregate, as sand or gravel. Okay, which are used as the as an ingredient in your concrete. Together with the cement, we are going to dissolve the cement into water so that the paste will act as a binding agent to the aggregate. Okay, so that if that will cure, then that will be a solid material. Okay, so that is the concrete. The properties of concrete depends on the ratio used in design mix. So actually the strength of that concrete is not fixed. Same thing with steel. We have what we call as grade of steel. That refers to the strength of the steel. That depends on the process also. If you want stronger steel, then the process will be a little bit costly compared to the weaker steel. In concrete, same thing. Okay, you need to adjust the ratio, the amount of concrete, the amount of cement, the amount of water. You need to adjust this one, and that will be discussed in your design subjects for you to have a higher strength compared to other type of mix or other ratio of mix. So this type of material is known in its high compressive strength. However, okay, so concrete is known to be high in compression strength. Okay. However, it is brittle and has limited tensile capacity. However, that is very, very weak. Okay, it can carry a tensile, but that is not much. Okay, since it is a brittle material, it cannot resist high tensile forces. So that is the weakest part of the concrete. Same thing in steel. There is a weak part that is expensive. Okay. So now, for us to have an economical, if you say economical, that is the most economical. If you say most economical, it means the cost should be least. Okay, that is the least cost, possible cost. Okay, for us to have the least possible cost or economical size or shape of these members, therefore, we have the previous idea is to combine. The idea which is done previously is to combine steel and concrete. Since steel is expensive, but that is strong in tensile, we are going to combine that one with concrete, which is a little bit low cost, but it is strong in compression, so that the concrete will work mostly on compression and the steel will work mostly on tension, and that is what we call as the reinforced concrete. Okay, reinforced concrete. So most of the time now, if tension is not common in that member, then we do not need to put steel. Just like on on pavements, on roads. In roads, actually, the scenario is that you have the pavement and the car is passing above. So actually, those are mainly compression forces. So actually, if you will try to look at the actual construction of pavements, there are no reinforcement. There are no steel reinforcement. Okay, since again, the tensile is not that high on the pavement, on that type of member. But on columns and beams, especially on beams, because the beams will bend. Okay, so there is a part on that beam that will be carrying tensile load. Okay, and that is again discussed in your mechanics. Okay, so that's why we are going to reinforce that one by steel to carry the tension. So actually, that is the explanation of this one. Now, let's move on the other commonly used type of material. Okay, so third there is the wood. It is an economically feasible natural material which is known with its lightweight and machinable property. Okay, so wood is a lightweight material. Yes, true. Compared to concrete and steel, wood is lightweight. Okay, and at the same time machinable. If you say machinable, that could be shaped by a machine. Okay, wood could be shaped using machines. So you can shape that one into a shape that you intended. It also provides good insulation from the cold, which makes it excellent in building materials for homes and residential buildings. So these are common on residential. If you say residential, that is for dwellings, family dwellings purposes. But for commercial, if you say commercial buildings, those are big, large buildings or high-rise buildings. These are not that common, this type of wood. It will not be used as a column, or it will not be used as beams. Because, if you will try to read the next, however, because of its lightweight, okay, since that is lightweight, wood is not the most suitable construction material to support heavy loads. It cannot resist heavy loads, and at the same time, not ideal for long span members. So that is the disadvantage of wood. But the advantage of that is it is machinable and it is lightweight. That's why most of the cases we are using woods in the trusses, because that is a lightweight material for you to add on the weight of the total building. Okay, instead of concrete. If you have a good supply of wood, you can use that one as the truss of the building. However, there are one more disadvantage of wood that I did not specify here, is the what do you call this one? What is my term for that? The okay, it is prone. Okay, it is prone to a lot of aspects or a lot of factors. Just like it is prone to pests, and it is prone to decay. Okay, but if that is well treated, okay, if that wood is well treated, okay, by different methods, it can last through years. Okay, wood could last through years. That depends on how we will try to treat, or how we treat the wood material. But again, as I've said, that is prone to pest, and then that is prone to decay compared to concrete and steel. But of course, if you will discuss that one on construction materials and testing, it will be totally explained. Okay, the advantage and disadvantage of each of these material. And then last type that I will be discussing on the building material is the masonry. Okay, masonry construction is using individual units to build a structure that usually uses mortar to bound the units. Okay, so individual units. So for example, is this. These are individual units. So by the way, masonry materials include bricks, stones, glass block, and most common lately is the concrete block with reinforcing if required. Okay, so this is the most modern, okay, most modern masonry, which is made up of concrete, and if you need a little bit of reinforcing, then you will be putting their reinforcement. But if the wall is actually not carrying a lateral loads, maybe that is just be needing the mortar. Mortar is the fillings. Okay, these are the mortar, the fillings that will bind these individual bricks or individual hollow blocks. Okay, so this is a highly durable, fire-resistant material. However, it can be sensitive to mortar and workmanship quality. If you say sensitive to mortar, okay, the issue here is that the mortar might not be able to hold this brick together. Okay, so that is the one challenge in using bricks or in using masonry. And then one other problem there is the workmanship quality. If your mason is a skilled person, then you might end up with this type of work. But if they are not that skilled, then you are now having problems with the aesthetics. Okay, how it looks like after the masonry is built. So that is the challenge in the masonry. The what do you call this one? The combination or the what do you call this one? Yes. The binding of each and every of the units, that is the problem, and at the same time the workmanship quality. Okay, so those are the most commonly building materials that I can discuss for this presentation, but there are a lot. Okay, so this is the end of this presentation or this discussion, unit 1, which is the introduction to structural engineering. So let me just review some of the concepts. So structural engineering, based on our discussion, is the study of the behavior of structures under effects of external loading, from stress distribution to design of each element with respect to the type of material used and its property. So again, what does that mean? Structural engineering is actually the study of the structure, from the way it will handle the loading applied and to the way it will react member by member. So we are going what we call this one as going to design each member to resist this type of loading. And in designing this member, we need to take into consideration the load itself, the type of load it is carrying, and then of course the type of material we are using. Okay, so that is where the properties of material will come in. So that is now the end of the discussion. So if you have any question, you may ask that one during the next live meeting. Okay, you will be asking that one on the next live meeting, or you can comment that one below the discussion. So thank you very much for watching. Okay, by the way, thanks for this free slide shares, okay, by Slides Carnival. So thank you very much for watching.